my last series of lectures, I went through one-dimensional motion with constant acceleration. We saw over the course of those lectures that motion is perfectly described by the kinematics equations. And then we applied those kinematics equations to describe what happens when cars are slowing down, rocket ships are accelerating, people are walking back and forth in front of the desk, and so on. That's all fine and good, but frankly, so what? What does that ultimately tell us about reality? That is, what does it tell us about the natural world? What does it tell us about the universe? Well, now we get back to Galileo. Recall, first of all, the following, that is, with respect to motion, according to the ancient Greeks, near the surface of the earth. According to the ancient Greeks, heavier objects fall faster than lighter objects. As a refresher, go ahead and watch my demonstration video once again called Do Heavier Objects Fall Faster Than Lighter Objects? As I previously have noted, the ancient Greeks, of course, are given a lot of credit with respect to the beginnings of science, but they made some mistakes. With respect to the scientific method, they never did any experiments. In that demonstration video, I do a simple experiment that begins to show that there is something wrong with respect to that statement about motion near the surface of the earth, according to the ancient Greeks. Galileo Galilei, the Italian astronomer and physicist in the early 17th century, was literally the first to realize what everybody here now takes simply for granted. Ultimately, it is air resistance that slows down falling objects, such as the piece of paper prior to me crumpling it up in that demonstration. So Galileo, however, goes one step further. He basically asks the following question: what would happen to a falling object in the absence of air resistance? Now, by posing this question, Galileo is also conceiving the idea of a vacuum, a region of space where there is no air. More than 400 years ago, that was somewhat of a difficult concept for people to wrap their heads around. How can you envision, for example, a region of space where there is no atmosphere? Galileo was the first to hypothesize the existence of such a region of space. Now, in order to answer this question, however, he devises a very simple experiment. Galileo is extremely important in terms of the history of the scientific method because he was one of the first people to do comprehensive experiments and then base his conclusions upon his experimental results. Now, Galileo certainly couldn't produce a vacuum in his simple laboratory. He could only imagine one and approximate one as best he could. Here's what he did. He first of all took an inclined plane and he made it as smooth as he possibly could. He did so to try to remove friction as much as he could. He tried to mimic a frictionless surface. As we'll see later on, there's no such thing as a frictionless surface, but Galileo tried to approximate one as best he could. Okay, so right here, for example, is an inclined plane. And he tried to mimic as best he could a frictionless surface. Okay, then he takes an object like so. He then positions the object on the inclined plane and he releases the object from rest. And then using the one-dimensional motion with constant acceleration kinematics equations, which he himself derived, he then measured the acceleration. So the object is released from rest. It accelerates in this direction. And he measured. The acceleration. So very simply, his experiment really just consisted of the following. Right here is an inclined plane, this board, it's fairly smooth. And then right here is an object, for example, this paper clip. And then he takes the object, sets it here on the inclined plane, and he then measured the acceleration. Let me jump immediately to his experimental result. Regardless of the weight of the object, the acceleration was always the same constant value. regardless of the object's weight, the acceleration was the same constant value. So for example, with my paper clips, I have here two paper clips. One is rather small, the other is rather large. And then you set up the inclined plane like so. You then take one of the objects, release it from rest, measure the acceleration. Repeat the experiment with the other object of different weight, release it from rest, measure the acceleration. The acceleration's values were the same thing. And then what he did is he repeated the experiment. He then took the inclined plane and he inclined it like so at a greater value of angle of inclination. And then what he did was he measured the accelerations again, and he got the same result. Regardless of the object's weight, the acceleration was the same value. It was a bigger value than it would be at a shallower angle, but the result was the same as before in the sense that the acceleration was the same regardless of weight. So do this, for example, with the large paper clip, like so, measure the acceleration. Do the same thing with the small paper clip, like so, measure the acceleration, and the accelerations were the same value. Therefore, what can you conclude from these experimental results? Well, now imagine taking the inclined plane and tilting it such that it's vertical. And remember that there is no friction. This then means that there is the same thing as saying that there is no air resistance. And then you take the two objects and you release them from rest at the same height and let go of them at the same time. And lo and behold, they hit the desk at the same time. This then means that all objects, regardless of weight, fall with the same constant acceleration in the absence of air resistance. This is the experimental conclusion that you reach from this data, from the experimental result. Let me briefly summarize that here. So Galileo repeated the experiment. At a greater angle of inclination. And the result was the same, just at a greater value of acceleration. Therefore, we can conclude the following. All objects, regardless of weight, fall with the same constant acceleration in the absence of air resistance. So Galileo experimentally overturns that statement about motion according to the ancient Greeks. No, heavier objects do not fall faster than lighter objects. Instead, all objects, regardless of weight, fall with the same constant acceleration in the absence of air resistance. In the course of doing these experiments, Galileo measured what that acceleration is. That acceleration is very important when describing motion near the surface of the Earth. It's given its own name and its own symbol. It's referred to as acceleration due to gravity. It is not referred to as gravity. It is called acceleration due to gravity. Acceleration due to gravity is given its own symbol. It's referred to as small g, as eventually, or rather as originally, measured by Galileo in the course of doing his experiments. That value is 9.8 meters per second squared. That's in metric SI units. Incidentally, by the way, the SI abbreviation stands for System International. In French, metric SI units is the standard that is used throughout the scientific world. In the old style English or imperial units, the value of G is 32 feet per second squared. Okay, now at this point, what I want you to do is pause this lecture, and I want you to go ahead and take a look at the free fall demonstration video that I've posted for you. Okay, now that you've seen that demonstration video is a more modern version, if you will, of Galileo's experiment. By means of the vacuum pump, I can go ahead and remove air resistance from the tube. If I do, in fact, remove all of the air from the tube, then the acceleration of the penny and the feather is exactly the same, 9.8 meters per second squared. Now let me go ahead and clear up some confusion that you may have about this value, acceleration due to gravity. For example, let's say that I take an object and I drop it from rest like so. As soon as I do, as long as we ignore air resistance, it accelerates downwards at 9.8 meters per second squared. If I take the object and instead I throw it downwards, like so, while it's in my hand, the object is not in free fall, as we say. Instead, however, the instant I let go of it, it's in free fall, and then therefore it accelerates downwards at 9.8 meters per second squared. While it hits the ground, it may be moving at a greater speed than it would be had I just dropped the object from rest, but while it's in free fall, after I let go of it, the acceleration is downwards at 9.8 meters per second squared. Those two situations are usually rather easy to describe. However, what trips up a lot of introductory students is the following. If I take an object and I toss it upwards vertically, like so, while it's moving upwards, is it still accelerating downwards at 9.8 meters per second squared? Absolutely. There is nothing different about the Earth's gravity. It is still the same Earth, regardless as to whether or not the object is moving upwards or downwards. The whole time that it's in free fall, it's accelerating downwards at 9.8 meters per second squared. If you're having trouble visualizing that, here's an easy way to describe this. Okay, so throw an object upwards. When I do, I give it an initial velocity vector v0 that looks something like this. And then let's say that as it moves upwards, it's slowing down. So a few moments later, let's say the velocity vector v looks like this. Okay, on this simple vector diagram, using the tail-to-tip method of vector addition, where is the delta v vector? That is the change in velocity vector. The delta v vector looks like this, like so. Recall that initial plus change is equal to final. So the initial velocity plus the change in velocity is equal to the final velocity. The delta v vector points downwards. The reason why I'm pointing this out is because remember that acceleration is change in velocity with respect to time. So then therefore the direction of the acceleration vector is always the same as the direction of the delta v vector. The acceleration vector is downwards at a value of g equal to 9.8 meters per second squared. Once again, there's nothing different about the Earth while the object is moving upwards as opposed to downwards. The whole time the acceleration is downwards at 9.8 meters per second squared. Okay, this concludes the lecture on free fall for part 1.